Okay. Hello, everyone. My name is Koyashi. I was a master student of SIT and UCS when this work was done. Now I'm an algorithm engineer at AutoNavi of Alibaba Group. Today, I will share with you our work about intra-urban region-based traffic flow predictions based on spatial temporal graph convolutional network enhanced by spatial context. My presentation has 6 parts, which are corresponding to the structure of our paper. Traffic flow predictions tasks can be divided into two types, network-based and region-based predictions. In this study, we mainly focus on region-based traffic flow prediction. Intra-urban region-based traffic flow prediction is to predict the future traffic inflow and outflow in each region of the city. The region-based traffic flow can be computed from the foreign car data, shared bicycle data, mobile phone data, and etc. Knowing the future region-based traffic flow accurately, travelers can make better plans, governments can take effective control measures to avoid large crowds of people. For enterprise, they can dynamically allocate transportation results, such as taxi and share bicycles. So it is essential for intra-urban region-based traffic flow prediction. However, traffic flow prediction is challenging owing to the complex spatial temporal dependencies in traffic data. On the one hand, the traffic flows of a region are correlated with its historical traffic flows because of autocorrelation of time series. On the other hand, the traffic flows of a region are also correlated with those of its adjacent regions. In addition, environmental factors such as temperature and rainfall can also affect people movement and thus affect the inflows and outflows of the regions. Early studies mainly use classical statistical methods and machine learning methods for traffic flow predictions. However, these studies ignore spatial features and do not model the complex spatial temporal dependencies, which limits the prediction performance. In recent years, many deep learning-based methods are proposed for region-based traffic flow prediction. Basically, we can partition a city into a grid map. The traffic inflow and outflow of a grid map can be treated as an image with multiple channels. By given a set of historical images as an input, a feasible schema is using deep learning methods to predict the future image. A famous model named ST-ResNet used several stacking RES units to model spatial temporal features at multiple time scales. But ST-ResNet can now well model the sequential features. To better model the spatial and temporal sequential features, one category of the study is to use different structure of convolutions. For example, ST3DNet used 3D convolutions to model the sequential features and the spatial features. But 3D convolutions are ineffective and cannot well model long-range sequential features. Another category is using CN or GCN with RN for modeling the spatial temporal dependencies, such as STDN and STMGCN. The spatial context can carry essential information about traffic flow change in the adjacent regions and help improve the spatial temporal predictions. However, in these studies, when modeling the temporal dependencies, they do not well utilize the spatial context. For spatial dependency modeling, most of them only model the adjacent relationships. Even in STMGCN, they build different relation graphs to model multiple relationships between regions, which increase the convolution computation several times and thus increase the model complexity. Before further introducing our work, we first introduce some basic concepts and give the problem definition. Basically, a city can be divided into an I multiply J grid map based on longitude and latitudes. Then we define every grid of the city as a region. For each region ij, we can compute the respective inflow and outflow by the entering flow and leaving flow at time interval t. So for the whole grid map, we can get the responding region-based traffic flow matrix ST with the size of I multiply J multiply 2. Therefore, the region-based traffic flow predictions can be defined as follows. Given historical traffic flow matrix of the city, our prediction target is to learn a function f to predict the inflow and outflow of each region in the city. To tackle the two issues we mentioned before, we propose a spatial temporal graph convolution network that is enhanced by spatial context. We name it as STGCN-SC. The figure is the model framework of our proposed model. This model mainly has three parts: temporal dependency modeling, spatial dependency modeling, and data fusion. The spatial dependency modeling includes the graph construction module. Here we utilize a sequential modeling strategies to model the spatial and temporal dependencies. Our contributions fall in the spatial and temporal dependency modeling. For temporal dependency modeling, we propose SCLCM to well utilize the spatial context. For spatial dependency modeling, we design a graph construction matrix to model both the adjacent and symmetric relationships. Here, the symmetric relationships mean the similarity between traffic-flow sequence. In the following, I will introduce these three parts in detail. Let's see an example first. There are traffic flow sequence of some adjacent regions. We can find that although region 65 and region 66 are neighbors, they totally have very different traffic flow patterns. Keeping the graph edge between the adjacent but dissimilar regions may transit for signals and may hurt performance. From another perspective, the distant regions can have similar flow patterns and cross relations. Adding graph edge between these similar regions, whether they are neighbors, can help predict the traffic flow change from a globally spatial perspective. So here, we build a relation graph to model both the adjacent relationship and the symmetric relationship. Based on the adjacent relationship, we can get the responding adjacent matrix AADJ. To model the symmetric relationship, we design a similarity algorithm to compute the pattern similarity Wij between region I and region J. If the pattern similarity Wij is higher than the threshold theta, we add an edge between region I and region J. To reduce the model complexity, we finally divide the graph adjacent matrix by combining two types of relationships. We use different thresholds theta1 and theta2 for different parts of the equation due to the inconsistent effects of the distance between adjacent and non-adjacent regions. When theta1 equals theta2, the equation denotes a spatial case of only considering the symmetric relationships. The proposed graph construction matrix has two main advantages. First, removing the attention on the adjacent but dissimilar regions can help eliminate the transmission of uncorrelated signals. Second, considering the symmetric relationships among distant regions can help model the long-range spatial correlations and capture the traffic flow patterns effectively from a globally spatial perspective instead of merely from a locally spatial perspective. Sequential modeling strategy is usually used for spatial and temporal dependency modeling. With the use of sequential modeling strategies, the spatial temporal distribution of the data may be changed after modeling the temporal dependencies. Thus, the following spatial dependency modeling module is facing the changed spatial dependencies that may be different from the correlation of input features among regions. This makes modeling challenges. So when modeling the temporal dependencies, if we can utilize the spatial information, these issues can be solved to some extent. Therefore, we propose a network named SCLCM to utilize the spatial context, which ensures spatial perception of each region while modeling the temporal dependencies. We here use several graph convolutional layers that are approximated by Chebyshev polynomials to extract the spatial context. To enhance the model performance, we follow the recent studies and do some data fusion. We first concentrate historical traffic flow sequence at different time scales to a new sequence as a model input. This is because traffic flows have parodic patterns at different time scales, and can be easily affected by past several hours, same timestamp of past few days and past few weeks. We also model the environmental factors by using fully connected network, as these factors can also affect human movement. The respective prediction results based on the historical traffic flows and external features are then added together as the final results of the prediction model. To prove the effectiveness of our proposed model, we then do some experiments on two public data sets, the bi-NYC dataset and the taxi Beijing dataset. In the bi-NYC dataset, the city is divided into a grid map of size 16 multiplied 8. In the taxi Beijing dataset, the city is divided into 32 multiplied 32 grids. Each dataset includes some external features, such as if it is a holiday, the type of the weathers, the temperature, and the wind speed. We select the last 10 days as the testing set for the bi-NYC dataset and the last 28 days for the taxi Beijing dataset. As shown in the table, our model outperforms 3 traditional models and several deep learning models. By additionally modeling 2 types of relationships between regions, the proposed model further reduced the RMSE error, achieving RMSE reduction of 4.8% and 5.7% for the bi-NYC and taxi Beijing datasets, respectively. For the bi-NYC dataset, when θ1 equals 0.2 and θ2 equals 0.8, the ST-GCN-SC achieves the best performance. That means the model ignores some adjacent regions with very large similarities and try to learn information from some non-adjacent regions with very high similarities. For the taxi Beijing dataset, the best θ1 is 0.5 and the best θ2 is 0.3. That means the model is trying to learn spatial features from a larger spatial perspective. We also do some aberration experiments to prove the effectiveness of the spatial context when modeling the temporal dependency. The SC-LSTM outperforms the LSTM and the ST-GCN-SC outperforms the ST-GCN. This proves that the spatial context is significant for temporal dependency modeling. Even the independently used SC-LSTM can achieve well prediction performance. However, by comparing the prediction performance between SC-LSTM and ST-GCN-SC, we can find that the spatial dependency modeling is still indispensable for spatial temporal prediction. Let's make a summary. In this study, we proposed a model named ST-GCN-SC to learn the spatial and temporal sequential features for short-term region-based traffic flow prediction. Our contributions are as follows. To utilize the spatial context when modeling the temporal dependency, we propose a network named SC-LSTM. Second, we design a histogram-based similarity algorithm to compute the semantic similarity between regions. Then a graph construction matrix is proposed for modeling both the adjacent and semantic relationships. Dynamic time mapping algorithm is commonly used to calculate the similarity between 2 time series. However, in this study, based on some experiments, we find that the DTW algorithm does not perform well when applied to the graph construction. In the future, we will continue to evaluate other similarity algorithms for the graph construction and consider to automatically build the relation graph. We also plan to study how to parallelly model the spatial and temporal dependencies as the spatial and temporal dependencies are coupled. That's all. Thank you.
Okay, thank you, Guikai, for your great presentation. So, any questions for audience? Okay, let me ask our first question. Maybe this is a very simple question. I just want to know, you mentioned that you construct the semantic relationships across different grids, that is your regions. So can you illustrate more about how the semantic relationship is constructed?
Okay. Just actually, we for each region we can get the responding info sequence and output sequence. So we construct a histogram from the info sequence and the output sequence. Then we compute the histogram similarity between two regions, and then we average the input the info histogram similarity and the output histogram similarities. I can show you the algorithm. This is the detail in the paper.
Okay, thank you. Okay, we have another question. Could you explain why this is no flow between forest and urban building, just like figure shows?
I don't get the answer. Get the question clear.
Yes, I also didn't understand Kerry. Yugu, can you speak? So what is the forest and the urban building means? This is a figure.
But it is no.
Can
Okay. It is just an example. This is because we assume region A with high flow and region B with no flow. This is only it is just an example. From this figure, we can know that if we region A and region B with very different traffic flow patterns, then we don't add an edge between region A and region B. Do I answer your question?